Hi everyone, welcome to The Witch's Tech. I'm Lachelle Foley. Today's video is about Internet Protocol, and although that says a brief overview, it may not be all that brief because there's a lot to the Internet Protocol. There will be a new playlist called Background, so most of the point of this channel is to show you how to do things. But sometimes it's nice to have a better idea of, why you're doing what you're doing. So I'm going to make these videos that are deeper dives into some of the topics that are relevant to the other videos. Again, I'm going to assume that you have very little background knowledge. As usual, please like and subscribe if you are likely to do such a thing. If you would like to donate, we are a 501c3 organization, AthensAreaPagans.org/donate. If you would like to just learn about us, AthensAreaPagans.org, and there are QR codes that you can use to get to those addresses as well. So, Internet Protocol. This is the reason that it's called the Internet. So, the Internet Protocol was first, and the Internet sort of happened later. So, Internet Protocol is a very common communication protocol because the Internet is all over the place and everywhere. It is the reason that your IP address looks the way it does. So, for example, your IP address might be 192.168.1.160, and I'm focusing here on IPv4, but that's the reason that your IP address looks that way. By the way, IPv6 is similar. We'll talk a little bit more about that later. It's more complex, and it's more capable, and it's more useful to people who are going to do networking for a living. So if you're sort of new here, you're more likely to run into IPv4 still for the foreseeable future. So it's a good thing for you to understand IPv4 first. So one of the things that Internet Protocol does is it bridges different networks. You might have a network in your house, and the computers in your house can all talk to each other, and you have a network at school, and the computers can talk to each other there, and maybe there's a network at a business, and the computers talk to each other there. Internet Protocol its purpose is to allow all of those different networks to still maintain their autonomy and maintain their separateness, but to be able to talk to each other. Another thing that Internet Protocol does is it decouples this communication from the hardware. So it doesn't matter what the hardware is, you can still use the same Internet Protocol to talk. Your house probably has Wi-Fi. Your office building might have wired internet access. And I'm not kidding, you can do Internet Protocol over ham radio. That's amateur radio to most of the world. It doesn't matter what the hardware is, the Internet Protocol stays the same, so it's decoupled from the hardware. By the way, I looked for IP over telegraph and I could not find it. I found telegraph over IP, but not the other way around. And to be honest, I'm a little disappointed in the interwebs, but whatever. No IP over telegraph. So, Internet Protocol is in OSI Layer 3. I want to talk about these OSI layers just a little bit, and we're going to start at the bottom of this slide and go up. So at the very bottom of this slide, OSI stands for Open Systems Interconnection, and those are the people who came up with these layers, and they're pretty useful layers. If you're ever going to get a job in networking or doing any sort of networking, you're going to want to know what these layers are. You're going to want to understand them. So let's start with Layer 1. Layer 1 is the physical hardware. So this is a switch, I believe, I'm going to go with Cambrian. And this is a router from the Cretaceous. And they are both connected to each other by an Ethernet cable. And, they are able to talk to each other. Oh, probably they would be. I don't know where the power cord is for this right now. Anyway, they should be able to talk to each other, and people do that on purpose. They try to make sure that things are backwards compatible because you don't want to suddenly cut people off just because they've got old stuff, right? Anyway, the physical hardware is Layer 1. These things have to be able to talk to each other, and so they need software that does understand the hardware. There has to be software that understands both of the types of hardware and can make them talk to each other. That is Layer 2. It's called the data link. So it's linking the hardware together. So Ethernet, the word Ethernet, that is that Layer 2. Layer 2 ARP, Address Resolution Protocol, that if you ever use Wireshark, which is a monitor of mostly layer 2 traffic, you will see that computers are very, very chatty. Oh man, they talk a lot. Anyway, the data link layer 2 is the software that allows them to talk to each other, but it's also the software that allows there to be a decoupling to layer 3, the internet protocol. And that's because there's an interface that understands internet protocol, and so internet protocol can do what it has to do without having to worry. And internet protocol is in OSI layer 3. There are other OSI layers, and I'm going to give you the proper names for them, and then I'll give you an analogy that I think will make them make a little bit more sense to you. So start at the top here, layers 5, 6, and 7, that's your application layer. That's what you want to talk about. Sort of more or less, that's in layers 5, 6, and 7. Layer 4 is transport. That's a protocol for how do you get stuff, how do you package what you want to talk about? How do you move it around? The internet, layer 3, that says, okay, I've got something here and I want it to get over here. How do I get it from here to here? The link layer, like we talked about before, that allows the actual hardware to talk to each other. And then at the very bottom, the physical layer is the hardware. It's now going to give you an imperfect analogy. All analogies are imperfect. Parcel delivery. If you want to deliver a package of some sort, piece of mail, box, whatever it is, layers 5, 6, and 7, that's the parcel. The parcel with its bubble wrap and outer wrap or whatever it is that makes your parcel. That's layers 5, 6, and 7. That's the thing you want to deliver, the thing you want to move. Layer 4 is kind of like the vehicle. Do you need a truck? You want to put it in a car? Do you want it to go by bicycle courier? Is it going to go by drone? Right? Okay, so the vehicle is layer 4. That's the thing that's going to carry your parcel. Layer 3, the internet protocol, that is kind of like directions and maps and addresses. This says, okay, I'm at this address and I need to get to this address. And how do I get from this address to this address? That's what internet protocol tells you. Layer 2 is kind of like the traffic rules. If you're going from the internet, the interstate down to surface roads, or if you've got a traffic light or a stop sign, what are the things you have to do? Those are the traffic rules. That's sort of like layer 2, where the hardware talks to each other, can communicate. And then, of course, layer 1 is the streets. It's the actual hardware where all of the traffic happens. IP addresses. There's an example of one there, and I will use this same IP address as an example multiple times in this video. 192.168.200.12. It is an IPv4 address. We'll talk about IPv6 later, just a little bit. IP addresses are more like phone numbers than normal addresses, in that if you take your house and you pick it up and you move it somewhere else, you have to give your house a new address because your house is in a new location. But if you have your cell phone and you move to the next house to go visit your friend, you don't have to get a new phone number. You take your phone number with you. IP addresses are pretty much like that. They can move around. Now, there is some mapping between IP addresses and their location. Certain types or classes of IP address don't seem to move around a lot, right? And so you can sort of make maps, and there are companies that do this, and they have to update them pretty often because the IP addresses do move around. Anyway, IP addresses closer to phone numbers than they are to physical addresses. We have an IPv4 address, and that's what we're talking about right now, Internet Protocol version 4 address, 192.168.200.12. That's an example. You have 4 numbers separated by dots. The minimum that those 4 numbers can be are zeros. So you can have the minimum is 0.0.0.0. The maximum that those 4 numbers can be is 255. So you have 255.255.255.255 is the maximum number. The total number of addresses comes from the fact that you can have 256 integers at each location because you have 255 plus 0, so 0 is another integer. So you have a total of 256. Multiply those all together, you get about 4 billion, and that's about how many addresses you can get within the IP4 address system, and that's part of the reason IPv6 exists, is because we were running out of IPv4 addresses. But you might be wondering, how come the biggest number is 255? If we're running out of addresses, why can't we just make the biggest number 2000 or something? Why does it have to be 255? To understand that, you have to know that the IPv address is not a decimal number. It's cast in decimal terms because decimal is something we understand. We know how to say 192 or 200 or 12. But that number is actually a binary number. It's just being represented in decimal for convenience. It's actually a binary number. So let's talk about what binary numbers are, because I imagine if you are here, you don't think about binary numbers very often. So in a computer, you have bits, and they can either be up or down or on or off or open or closed or whatever, happens to happen in your situation. The values can be 1 or 0, two values, binary. If you want to count in decimal, decimal has 10 integers, 0 through 9. And once you've exhausted those 10 integers, if you want to actually represent the number 10, you have to have two decimals, so you can have a 1 and a 0 to represent 10, right? 0 through 9 are the 10 integers, but if you want to represent the number 10, you need two integers. Binary works exactly the same way, and all of the other integer-based counting systems work the same way. It's just that binary's only got two, so you go 0, 1, and then you have to go 1, 0, and 1, 1, and now you're out of space, and you have to go 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, etc. Of note, if you have three spaces, so where I just was, 1, 1, 1, three spaces, you can represent 8 numbers with 3 spaces. But if you want to represent the number 8, you need 4 spaces. And so you see I've listed the decimal numbers 0 through 10 and the binary 0 through 10. So hopefully you're a little bit more comfortable with binary numbers. And the main thing you want to know is when you see a binary number, you may not be able to look at it and just tell what number it is, but it's just a number. It's just an integer. It might be a big integer or a small integer, but it's just an integer. So don't worry about it, and you can figure out which integer it is if you need to. Plenty of ways to figure that out. So IPv4 addresses are actually binary, because in the hardware at that bottom level, that level 1, the hardware has these little switches. It's binary. So the dot decimal, that's what it's called, the dot decimal notation, 192.168.200.12, is actually the binary notation. This is what the number actually is. You have 8 binary digits, dot 8.8.8. So there's a total of 32. 8 times 4 is 32. Total of 32 binary digits split into 4 octets, so 4 sets of 8, and separated by zeros. To be a little complete about it, possibly overcomplete, if you have the dot decimal for 255.255.255.255, it's just a bunch of ones. The dot decimal for 0.0.0.0 is the same number of zeros. This is an image from Wikipedia, and the reference is at the bottom, so you can go and look up all of the information, including the license for using this image. It shows a different IPv4 address and its relationship to its binary. But if you notice on that one side, it says there's a most significant digit, and on the other end, there's a least significant digit. And what that's telling you is that's actually just one big number. And separated out into octets to make it easier to read, but it's a big number. Like if you represent a million by 1,000,000,000 to make it easy to read, this is just one great big number in binary. And we'll see that in just a moment, how it is. Quickly, IPv6 addresses. I'm not going to spend any more than this one slide on IPv6 addresses because we don't really need to right now. They are represented in hexadecimal. Hexadecimal is base 16. In order to get 16, we use the 0 through 9 digits for our decimal system And then we add A, B, C, D, E, F to get the extra 6. That gives us 16 digits that we can use. But the IPv6 address, even though it's represented in hexadecimal, it's still actually binary. So if you look at the example that starts with 2001, and understand that that is not 2001. That's a hexadecimal number. It is not 2001. It's something else. I'm sorry, I don't know what it is, but it's not that. And it is actually, if you look at all the ones and zeros down at the bottom, that's what that number actually is. It's a number in binary. In this case, you have sets of 16 binary digits, and there are 8 of them. By the way, the IPv6 addresses can be shortened. There are rules for shortening them. And the example, if you look below it, it can shorten to this shortened form. And we'll see that in a moment as well. Subnets are important. So subnets, 4 billion addresses is a big space, right? So maybe you want to use just a little piece of it. And there are reasons to want to do that. In fact, there's an organization that decides, oh, this part of the internet can be used for this, and this part can be used for that sort of thing. IP subnets are logical network subdivisions. And when I say logical, I don't mean, oh, that's logical. I mean, as in it's computer logic, it's instructions. So you have instructed a set of computers to use the same portion of the network address space. So a subnet is a little portion of the address space, and you define it, and then you say, okay, you computers, you are using this little piece of the address space. So if you have seen something like 192.168.200.12/24, that was defining a subnet. It was also defining an address and the subnet. You might have also been told your address is 192.168.200.12, and then told that your net mask is 255.255.255.0. These are the same thing. The one that ends with /24 and the one with all the 255s, those mean exactly the same thing. And we'll see why shortly. And we'll see a lot of it right now. So again, to understand it, you have to understand that this is not actually a decimal number. It's a binary number. The 24 is a decimal number, but what it's telling you is the first number, how many of the first digits do not change. So when you have /24, it means that the first 24 of the binary digits are not going to change in this subnet. That means that only the last 8 can change. And so I've reproduced the decimal representation below. It's on the slide before. It is important to note that for the /24, that type of notation, all of the numbers 0 through 32, so 0 or all 32 of the spaces, all of those numbers are valid. Not all decimal numbers are valid. And that's because of how the translation happens between the binary and the decimal. And I'm not going to go into that any further, but if you really want to understand it, I promise you can just go think about it a bit. And if you need help, let me know. I can probably help. Of importance to this notion of subnets is the private networks. Private networks are set aside for use in local settings, like your home, your office, etc. There are 3 ranges that are allowed: 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. Together, these make about 18 million addresses. 18 million addresses is enough for most people in most situations. And if you have a really big organization and you need more than 18 million addresses, that is beyond the scope of this video, but it can happen. Trust me, it can. 18 million is enough for most people, though. By the way, by default, your router, the router that you buy to put at your house, the router that talks to the rest of the internet and then talks to your house, on the rest of the internet side, if it gets any sort of communication from one of these private networks, it will reject it. It won't allow it because it says this is wrong. It should not be out there. It's only a private network. While we're talking about gateways and routers. So a router is a thing that routes traffic between 2 networks. A gateway is something you think about when you're on the inside of the network, the inside, the local side of the network. So the local area network, the LAN, L-A-N, local area network, that's sort of the inside, the private side of the routers. That's what's in your house. From all of the computers in your house, from their viewpoint, the gateway is whatever IP address you've assigned. The router, by default, usually the first or perhaps the last available address in the subnet is chosen. Doesn't have to be at all. So typically, if your house is in the 192.168.200.0/24 subnet, the gateway IP, your first guess would probably be 192.168.200.1. The external IP is going to be whatever your internet service provider has told you it is, and you just assign it and give it the net mask. And by the way, if you're having trouble, ask your ISP to give you the net mask, because sometimes you need to ask them. So, assigning IP addresses inside your house or wherever you're going to assign it, they have to fit the subnet. And not only that, but it's not just that the IP address has to be part of the subnet, but you have to tell the computer the correct subnet and everything, because if the computer tries to talk to another computer, even if they're sort of in the same subnet, in terms of the IP addresses are in their subnets, but they're two different subnets, which can happen, they won't talk to each other. They'll say, no, we're not in the same subnet. So when you have computers that you want to communicate with each other, they need to be in the same network, or they need to have routers who can connect them. So in your house, if you have the same subnet we've been talking about, 192.168.200.0/24, the addresses have to range from all of the masked part .1 to the masked .254. The first and the last are reserved for the network and the broadcast, and I'm not going to explain what those are, but just accept that. The first and the last you can't use for an address, and you can use all the others. If you want to calculate these things, if you want to find out all this information, I know I've got this network, what can I do with it? There are utilities called IPCalc and SIPCalc, and I'm going to show those to you in just a moment here. IPCalc was made mostly for IPv4, and SIPCalc was made mostly for IPv6, but nowadays both of them do both, but they do that in slightly different ways. So let's go take a look at what they do. So, okay, I've got here IPCalc. I'm starting with IPCalc, and this is that same address and network that we've been talking about. So if I run this, IPCalc is going to say this is your address. It's also going to give me the address in binary. And it gives me a little space here, right? There's a little blank space there. And that is separating the masked part, the part that doesn't change, from the part that can change. The net mask, all of these ones cannot change, the zeros can change, and the wildcard is the opposite. The zeros cannot change, but the wildcard, this is the part that can change. It will show you the network that you're in. It will show you the minimum host and the maximum host and the broadcast. It will also tell you that this is a Class C private internet. By the way, this magenta highlighting is just because my syntax highlighter does not seem to know exactly what to do with the output from IPCalc, and that's okay. If you do SIPCalc, remember IPCalc was tuned for IPv4 and SIPCalc is tuned for IPv6. If you do the same thing, you will find that you get a lot of the same information, but you get some different stuff. So one thing that's interesting here, remember when I said that this number, this binary number, is just one big number? Okay, this in decimal is that number. So that number is that, whatever that is, and so 32 billion and something or another. Anyway, so that's that number in decimal. This is that same number in hexadecimal. Again, you get the network min, you get the mask, you get the network mask in the bits. So it gives sort of the same information, but importantly, it will tell you, just like the other one, here are the usable range. Here are the numbers that you can actually put in your network. And it'll tell you how many are available. Now I'm going to show you, so I was going to copy these in or type these in, but nah, let's don't do that. Okay, so now I'm going to do ipcalc on that hex. This is IPv6, so this is the one that's in hexadecimal. I'm going to give it a net mask of 64. So ipcalc on an IPv6 address. Remember, ipcalc was originally made for IPv4, but it has been extended to handle IPv6. And so it's doing sort of the same thing that it does. It gives you the address, it gives you the net mask, and it gives you the binary. This is that number in binary. So kind of interesting if you ever needed to know. So that's how I got the number in binary. I just let ipcalc tell me what it was. And if you use SIPCalc on the IPv6, it tells you that it's IPv6. It gives you the full expanded number. It also gives you the compressed number, and again gives you the network range and etc. Same sort of thing that you might find useful. Okay, so moving on to Bogon networks. All right, Bogon networks. Let's say that you have a bunch of computers, and you need some of them to be in one network, and you need some of them to be in another network, but you've only got one switch. You've got maybe a big, 32 port switch, and you've got all these computers, and you wonder, can I just hook them all into the switch, but still have them be in two separate networks, and can that work? And yes, it can totally work. You can definitely do that. And the computers, these will talk to each other, and these will talk to each other, and they will not talk, cross-talk. They will hear each other, though, because they're all in the same hardware. All of them are going to hear all of the crosstalk. So if you're doing this on purpose, that's legitimate. Sometimes this is a way that people will try to hack a system. So it's not always legitimate. And when a computer hears chatter on its network from something that's not part of its network, it will call that a bogon network. So we have a bogon message or whatever. Your logs will be just filled with, oh, I hear all these bogon cries for talk to me. Basically, computers are chatty. Oh my, they are chatty. So if you have done this on purpose, you can suppress those messages, not a problem. If you have not done it on purpose and you see these messages in your log, then something is wrong. Usually it's not that you've been hacked. Usually there was a mistake, or maybe a piece of hardware is having a bad hair day or something, and something's just doing something weird. But whatever it is, and if it's hacked, what it means is someone has come into your network and they've sort of hooked into your network, and they've made a separate network that's all their own, that's not yours, right? And they're doing something that you probably don't approve. So whatever the problem is, if you did not make this bogon network, you do want to find out what it is and you want to deal with it. Getting from one place to another is called routing. So getting from, I'm at this computer and I want to get a message to that computer. Routing is how you get from the one place to the other. You can specify routing a little bit in your local setting, but only a little bit, and that's on purpose. Mostly the routes that are used to get from one computer to another vary from moment to moment. They're calculated on the fly, and that's on purpose. Because let's say you are connecting from this computer to this computer, and you're going to go from this computer to this one to this one to this one to this one, and here you are at the end. What if one of those computers in the middle, what if there was a power outage or something went wrong with the computer? You don't want your internet traffic to be stopped just because you chose, a bad path for that particular day. So the internet, one of the things Internet Protocol does is it has the computers figure out how to get the packages from one place to the other. And so the routes will vary from time to time. And by the way, not every computer on the internet is a router, potentially every computer on the internet could be a router, but most are not, and that's probably just as well. It would probably just get really confusing otherwise. But you know, potentially every computer could route everything. That could totally happen. If you want to see routing, Traceroute will help you. And so hopefully I'm going to show you a Traceroute. So I'm going to traceroute to 8.8.8.8. This is a DNS server at Google, and Google gets hammered a lot by IT people trying to figure out if their computers work or what have you. And so far they've allowed us to do this. Thank you. We appreciate it. So if I hit traceroute on that, you're going to see different things happening. So you've got the gateway. So this is me from my computer going to the gateway. And then from the gateway goes out to Spectrum. And then, lots of stuff at Charter. And I don't know what that is. I'm not worried about it. Oh, that's milliseconds. That's part of this. It's hop number 10. So that it took, and you also get the timings, like how long it took for the things to happen, or how long it takes for a ping to happen. This computer is allowing traffic through, but just does not respond to any of that sort of information. When you get stars, you've got a computer that's just not going to respond to information. And then finally, you arrive at, the Google's DNS at 8.8.8.8. If you are having trouble getting out, sometimes it's useful to do a traceroute, because you might find that there's one computer that's always hanging up. And if you can figure out where that computer is from, and usually you can, find out, are y'all having a problem today or something? And maybe you can try to convince your computer to do something different. Can't always, but at least you can understand what's going on. Anyway, traceroute is a useful way to figure out what might be going wrong. And you know what? I did not show that to you. Sorry. Okay, let's try that again. Here's the traceroute, and it is now being shown to you. So what I was saying was, and there's the gateway coming out. Go to Spectrum. Here's a computer that doesn't talk to us. Here, a bunch of hops through Charter, which is a part of Spectrum. And here are the timings I was talking about, it's using something called ping to figure out timing. So it's for each computer, how long does it take to get to that computer? Here's another computer that will let traffic through, but does not respond to any of the requests for other information. And then finally, we're getting to Google, which is 8.8.8.8, and traceroute 8.8.8.8 is how I got there. Sorry for not having that be visible a moment ago. All right, so I'm going to talk a little bit about encryption right now. Encryption is important in general. Encryption happens, for the most part, somewhere inside of where the blue outline is. So somewhere it's actually in layers 4, 5, 6, and 7 is actually what's getting encrypted. It might be encrypted at the IP, the IP header may include the decryption information, or the encryption, whatever's necessary to let the other side decrypt. But it's always the data further up. The IP headers themselves cannot be encrypted, otherwise you don't know where anything's going to go. So it'd be like putting a piece of mail in the mailbox, but you encrypted the address. Your mail carrier is going to say, I don't know what to do with this, and give it back to you, right? So you have to have the IP address visible, and that concludes the main IP overview part, and I want to now spend a moment elaborating on encryption and IP addresses. But in order to do that, I want to take a slightly different tack to how we're doing it. So first off, I use my hacker outfit, right? It's almost little Red Riding Hacker, who you have to wear a hood, right? As part of being a hacker, you can't really do hacking right. Like, it just doesn't work. The computer refuses if you don't have a hood on. Glasses are optional, especially nice sunglasses and hard parts. And probably the crystal ball as an interface is a really unusual choice, but let's go with it now. So what I want to talk to you about right now, something dear to my heart, the dark web. I know it sounds scary. Very, very scary. I know. All you hear about is all bad things on the dark web, but there's no reason to be afraid of the dark. Really, there's not. Let's talk a little bit about the dark web. Also called the dark net. It rides on top of Internet Protocol. So Internet Protocol is there, but it's something called an overlay network. It uses Internet Protocol as the base on which it works. It is not part of the OSI layers. It is sort of outside of the OSI, so it's a layer that is not a layer for those of you who might understand that reference. One of the things that the dark net does that makes it so appealing to certain types of people is that it hides traffic movements. And if you wonder why that might be important, let's use a little analogy. So let's say I'm in class with my good friend Darkness, and way at the beginning of the year, the teacher separated us because she was always talking and giggling because, well, you know. And then they took our phones away. So we had to actually write notes and send notes. So everybody in the class, they all agreed that everyone was going to pass everybody else's notes because that's how the internet works, right? But the problem was, if the teacher ever happened to get one of those notes, it would always say, "To nameless from Darkness." And so the, teacher didn't care what we were talking about. Yes, we encrypted our communications. Every single one of them looked like we were talking about some cute guy, right? But the teacher didn't care. The problem was that we were talking to each other. And even if we could figure out a way to not put "To nameless from Darkness" on the outside of the note, still, after a while, the teacher could watch the notes moving around and just from analyzing the traffic and figure out who's talking to whom. And that can be a problem. Now, of course, it's a problem for the hackers and the people who want to steal your credit card and your social security number and do whatever else they do on the dark net. But the dark net is just a tool. Like any tool, it can be used for good or for bad. And sometimes the dark net is used for good. And here's an example of a time that the dark net is used for good. Let's say that you have witnessed some mean person engaging in some human rights atrocity, and you would like to tell someone about it, some authorities like the International Criminal Court, perhaps. You do not want the mean person to know that you are talking to the International Criminal Court. Mean person does not care what you are saying to the International Criminal Court. It doesn't matter at all. That you are talking to the International Criminal Court at all will ensure that the mean person wants to make your life very, very unpleasant and probably short. People who are in these sorts of situations also routinely use the dark web to communicate. And there are other reasons you might want to just hide your movements. There are legitimate reasons that don't involve spies and reporters. There are still reasons you might want to just hide. So, one day, we might all be using the dark net or something like it, some evolution of it, somehow. So, to close, I want to talk a little more soberly, I guess, about some history. So, back in the mid-90s-ish, there was something called Pretty Good Privacy. Mostly just gets called PGP. Came out. It is still pretty good privacy. Some of the implementation details have changed and it has evolved into different things, and other things are sort of based on it or inspired by it. But it's still pretty good. It was early encryption for the masses. So anyone, well, at least in the United States, it was illegal to export it outside of the United States at that time. But anyone in the United States could just download it and install it on their machine, and then they could encrypt messages and send the messages around. But a lot of the talk about the encryption was really very similar to the talk about the dark web. People were using it for bad things. They were using it to transmit pornography or people's credit card informations or to make drug deals or whatever it is that was not okay. Encryption was being used for that. So if that sounds sort of familiar, it's because it is. I mean, there's a lot of similarities between them. At the time, there was a counter movement. I was part of it, a very small part, because I was working on PhD, couldn't do a whole lot myself. But the counter movement was trying to get encryption to be just common, to be normal. So we had parties. I can't explain the parties without explaining the encryption, but trust us, we had parties that were about making encryption be normalized. We also were very conspicuous about our use of the encryption, and I promise you it was not easy to do this. To encrypt an email message at that time was really hard, really painful. So anyway, and I did it. My friends did it. But the thing is nowadays, if you go to a website and it doesn't start with HTTPS, your browser tries to tell you this is unsafe, go away. And that's encryption. That's what that is. You're just encrypting your communication. So nowadays, encryption is everywhere. And in your email, depending on how you do your email, probably your email is encrypted. In fact, I suspect that for most of us, to send an unencrypted email now would be harder than it was for us back then to send the encrypted email. So, 5 or 10 years down the road, we might be all on something that hides who we are and where we are and what we're doing. And with that, Benjamin Franklin Duck says, "Who has lightning bolt duck? Tell Benjamin Franklin Duck." And Masked Avenger Duck swoops in and says, "You there! You, sir! Are you a member of a Bogon network?" And Benjamin Franklin Duck says, "What? Why do you care? I don't understand this. Really, it doesn't make any sense."